Okay, so let's go back to our favorite water tank and see if the thermal wind relation actually works. So we looked at water, which has a temperature dependent density variation, and then we derived the shear of the geostrophic flow as a function of grad T. We'll see in the next slide that this is quite parallel to geostrophic velocity being the similar expression with grad P, right? So UG was 1 over rho F dP dx minus 1 over rho dP dy, and V was 1 over rho F dP dx, right? So here is our geostrophic equation and hydrostatic balance, which this can be written as UG 1 over F rho Z hat cross grad P, whereas when we do DUG DZ, the shear, then we had grad T with alpha and F here, alpha G over F, right? So you can see the parallel there. In the lab, basically they create a setup like this. There is water filled with water filled with something. The tank has a can in the middle with the edge of the can extending a little bit above the surface of the water. So they rotate the tank slowly and establish a solid body rotation, as we have talked several times before, where the entire water columns are moving with the same speed as the tank, so it's a solid body rotation. And slowly the can in the middle is filled with ice or ice water that creates a temperature gradient. So then the can of ice is going to introduce a temperature gradient, and a thermal wind shear develops just because of the temperature gradient. Okay, so 5 minutes are all that is needed to continued rotation to create the thermal wind in the lab, and we'll see something really cute happen. So they have dyes down the water column and paper dots floating on the surface to visualize the flow, but you can see the thermal gradient, thermal winds here already. Okay, so here near the surface, the currents are going in the same direction as omega, the rotation, but you can see they are faster in the direction of rotation than the tank. What does that mean? You have actually produced westerlies in the lab. How? We kept saying there are westerlies on the planet, but I hope some of you thought what that actually means. Westerlies means winds going from west to east. The planet is rotating from west to east, so you have winds going faster than the planet itself. If it happens above the surface, you think, okay, great. But when it happens near the surface against friction, then you have to say, where is this momentum coming from? We'll see that angular momentum is picked up in the low latitudes where the Earth's radius is much higher, and then it's exported to mid latitudes where the westerlies are, and then put down to the surface. So where the jet streams are, we saw the wind speeds are very strong, very high, whereas that can come all the way down to the surface and create westerlies. So that's how you also create westerlies here, and you can see that the winds fall off and actually go in the opposite direction at the bottom because of friction. And the other interesting thing we will see later on is that this also sets up a thermal circulation where near the cold part of the tank, water sinks. This thermal wind comes with this circulation. Water flows out, rises near the outer edge, and creates this cell. For some of you who know the circulation in the atmosphere, you probably know that that is like the Hadley cell, right? So there is a relation between Hadley cell, thermal winds, and so on. So dUg dz is alpha g over f z hat cross grad T. In the lab, we have set up this temperature gradient from the cold middle to the warmer outside, and you can clearly see this thermal wind being created with faster westerlies here. So that means cyclonic direction of the rotation and winds in the same direction, whereas here you have weakening winds all the way and some reversal as well. So in the spherical coordinate of this radial coordinate, it's not exactly spherical, in the water tank you can write it as dv theta dz instead of dug, because v theta is the azimuthal velocity, and alpha g or f grad t can be written as alpha g or 2 omega dt dr. Here you had dt dx dt dy, whereas here you just have the radial direction, which obviously can be split into x and y, but doesn't make sense in this context. Okay, so that's the vertical shear of the azimuthal velocity related to the radial gradient of temperature. Horizontal gradient of temperature is producing vertical shear in geostrophic winds. Okay, that's our favorite diagram we have been following all the time. So the thermal wind equations and the Taylor-Proudman theorem are related, basically because it's the geostrophic and hydrostatic balance together under horizontal gradients in temperature. Temperature in the atmosphere is important, so we keep saying thermal winds, but actually obviously it's related to dependence of density on temperature. Okay, so how does the fluid adjust on large scales when gravitational pull downward? When you tilt the air column, you have to somehow make sure that it doesn't keep tilting or tilt over. What counterbalances the rigidity of these Taylor columns? We will see that balance in the next podcast. Simple concepts, actually, just looking at this in the lab should create an image in your head that you can carry, that can easily help you remember the concepts. Just looking at the equations may not help, but looking at the actual zonal winds with the vertical increase in wind speeds, the westerlies, and the jet stream should help you. Plus these lab experiments should really cement the deal in your head, the concept in your head. I hope